The relative rates of substitution and elimination reactions also will help us determine which mechanism is followed or which reaction happens in different circumstances. Now, in our original chart of reactions and mechanism, we included only the substitution reactions, and we said that methyl or primary reactions go Sn1, tertiary goes Sn2, and then secondary is a tipping point where it could be Sn1 or Sn2 depending on the conditions of the solution. Now we will introduce an additional factor, specifically whether or not the nucleophile is a weak base or strongly basic. And we have a mantra to help us remember that strong bases favor elimination. The exception to that rule is that unless the leaving group is methyl or primary, in which case we're going to favor substitution. The exception to that rule, by the way, is that we can still get elimination to happen if we use a bulky base and or extra heat. So if you're doing a synthesis type problem with a primary leaving group, you really can choose substitution or elimination. But if you're predicting a product of a reaction of a primary leaving group with a strongly basic nucleophile, we want to pick the substitution product unless that base is extremely hindered. Now let's take a look at how we might apply some of these ideas to a couple examples. And we'll look here at a pair of reactions that start with alkyl bromides, both of which are reacted with potassium hydroxide. We're not given a solvent in either case. However, we're given a condensed version of our table for help. So let's pause the video here and see if you can predict products. Looking at our starting materials and our reagents, we find two things are important: the degree of substitution of the leaving group, which in the case of our first example is primary because the carbon the bromine is on has only one other carbon attached, and our nucleophile is at least as strongly basic as hydroxide or stronger. In fact, it is hydroxide, so we have a strong base present. So if we go down to our table, we find our primary leaving group. Under strong base, we find we're still going to predict substitution. And so our product would have our nucleophile, the OH-, in place of the Br. Now, just to give you an example of getting that reaction to undergo elimination, if we really wanted the alkene, we could use a bulky base like sodium tert butoxide and extra or increased heat. And we don't necessarily have to write all of that, but what we want to realize is if we really want that alkene, we can get it, but that if we're in our typical predictions, we're going to look towards that substitution. In our second example, we have a secondary leaving group. We still have the same strong base, and so we're going to find that with secondary and a strong base, we're going to favor elimination without an exception to that rule. Our regiochemistry, and it's worth noting here, right, we have hydrogens on either side of the carbon with the leaving group, and so we've got a question of regiochemistry. Which region of the product molecule do we want to put that double bond on? And we choose, according to Zaitsev's rule, the more substituted location to be the major product, although we would expect a little bit of the minor product as well. Would being the less substituted alkene. Now, if we had wanted to not favor elimination, but we wanted to favor substitution, with this same secondary leaving group, let's say we wanted to make the alcohol, then we would want to get substitution, we'd want a weakly basic nucleophile that was equivalent to hydroxide. And in this case, we could actually use water and do a solvolysis reaction, which, because water is a weak base, would favor substitution. It's going to, because it's also protic, it's going to go by the Sn1 mechanism, although that's not important for getting the product. But what it does tell us is that we have an alternative here that could get the substitution product instead. So we're using our understanding of rates to determine which mechanism will happen in given circumstances. And the mechanism that dominates is dominating because it's the faster of the two possible reactions. We can also make comparisons between the different molecules undergoing the same reaction. For example, in this case, we have 3 alcohols. Which one would dehydrate most quickly? Pause the video here and give it a try. Now note the difference in the starting materials is really primarily in the degree of substitution. We have a secondary alcohol, a primary alcohol, and a tertiary alcohol. These are under protic conditions, which favors carbocation mechanisms, just like Sn1. However, in this case, if we're doing dehydration, we're doing an elimination, so we don't have a nucleophile, but our rate of reaction is still going to be favoring formation of the more stable carbocation. And so our tertiary is going to be fastest, again, because we can make the more stable carbocation intermediate, and the rate limiting step, and these are going to tend, this is a condition that's favoring E1, the rate limiter is the formation of the carbocation. Now it's worth noting that the tertiary and the secondary are both going to go E1. The primary would still go E2 because we don't want a primary carbocation. And this is just like Sn1 and Sn2. But because our conditions are protic, we're favoring the carbocation mechanism, the E1, over the E2. And so we're following the rules of rate for the carbocation mechanism, which is, again, the formation of the more stable carbocation is what's going to make the reaction go faster.